Okay, yeah, we see that. All good.
Perfect. Good morning. Thank you very much for the invitation. I'm very happy to be here. What I want to present is, is joint work with Thomas Galli and Markus Muller, also speakers of this workshop. And I want to talk mostly about this paper, but I'm also going to mention results of these other two papers. Can you see my pointer?
Yeah.
Perfect. Okay, so my main claim is that the measurement postulates of quantum mechanics are redundant. What I mean by measurement postulates are actually three postulates. One that specifies the mathematical structure of measurements, namely that they are Hermitian operators, POVM, orthonormal basis, just pick your favorite one. The other postulate is that the formula for assigning probabilities, the Born rule, and the post-measurement state update rule. Okay, I'm claiming that these three postulates are redundant because they are a consequence of what we could call unitary quantum mechanics. With this, I'm not claiming that the role of measurements is unnecessary or less fundamental, as for instance in the many worlds interpretation of quantum mechanics, measurements are somehow a particular type of dynamics, so hence less fundamental. So I'm not claiming that here. All the contrary, here we take an operational approach where the notions of measurement and outcome probability are primitive, but we do not impose any particular structure on them. And then is the specification of this structure what is redundant? Okay. Okay, so I'm going to be more concrete. Let us remind the postulates of quantum mechanics. States are raised in Hilbert spaces. Here we are going to consider finite-dimensional Hilbert spaces, but also countably infinite dimensions. The dynamics or transformations is given by unitary matrices. The Hilbert space of a composite system is a tensor product of local Hilbert spaces. And let me just put in a compact way the measurement postulates with the following statement. So namely that outcomes are associated to Hermitian operators in this interval, so what we call POVM elements, and the probability of outcome Q when I prepare state psi is given by this formula. Sorry for repeating things that you know very well. So what we are going to consider here is what happens to theories that satisfy the first three postulates, this, and this, but they have an alternative measurement postulate. And to put an example of what we mean, I'm going to start by considering just one particular alternative measurement postulate, okay, which gives rise to a different theory that, as we will see, has properties that are radically different from quantum theory. Okay, so what we see here is something similar to the Born rule, but here there are the state that we are measuring, we have kind of two copies of it. Okay, so we have the tensor product of the projector onto psi 2 times. Okay, so then this outcome is represented by a matrix that acts on the symmetric subspace of two copies of the original Hilbert space on which we are interested. Okay, and the probability of this outcome when I prepare psi is given by this formula. The normalization condition is that if I sum over all the effects corresponding to one measurement, the probability must add up to 1, and this in terms of effects means that this sum has to be equal to the projector onto the symmetric subspace on these two copies of the Hilbert space. So here what we call the unit effect is this projector onto the symmetric subspace. And in quantum mechanics, it's just the identity, as you know very well. Okay, so the first thing that we see is that as soon as we change the Born rule, namely this, okay, the ensembles of pure states that are equivalent or not, the notion of equivalence changes. Okay, here we see that with this Born rule, two ensembles of pure states are going to be equivalent if they satisfy this condition, and hence the mixed states will no longer be density matrices, but these objects here. Sorry, these objects here. Okay. And this has very exotic consequences. For example, the fact that if I take a uniform mixture of up and down in a spin 1/2 particle, that's not the same as taking a uniform mixture of right and left. Also, no, 1 second. Yeah. Okay, so we have this. Some other exotic properties is that spin 1/2 particle, here it encodes 3 perfectly distinguishable states. Okay, not 2 as in quantum mechanics, but 3. And a general state, a general mixed state of a spin 1/2 particle, instead of having 3 real parameters, namely the block vector, we need to, in order to specify this state, we need 8 real parameters, not 3. So more exotic properties. Let's keep on with every time even more exotic properties. Yeah, so now let us analyze what happens in this alternative theory when we have bipartite systems. Okay, so we have Alice, Bob, they share this pure state. It's a bipartite pure state. And now we want to calculate the joint probability of having outcome F in Alice and outcome G in Bob. Okay, as we are going to see now, this cannot be given by this naive expression. Okay, because the symmetric projector into the global space Alice Bob is not the tensor product of the symmetric projectors of Alice and Bob. We also need the antisymmetric projectors. So then what would happen is that if we sum over all the outcomes, let's suppose that this is I for F and J for Bob, if we sum over all ij, we should get a unit probability, but this is going to get just this part. It's not going to get the global unit effect, but also this part. So this state is going to have support here, and hence it will not, adding all these probabilities will not add up to 1. Okay, so this is clearly inconsistent. So this is not a valid composition rule for FX. One consequence of this is that this theory violates local tomography. Okay, so if Alice and Bob share an arbitrary state, a mixed state of 2 parties, in order to determine this state, even if they have many copies, it's not enough in this theory to make local measurements. Alice and Bob need to bring the 2 subsystems together and do joint measurements. Okay. Okay, but actually, okay, so we know that this is not the right composition rule, but it turns out that the only consistent composition rule is unique. Okay, and it's this one. Okay, so the way we compose effects, and we call it the star product, is given by this formula. And this formula is uniquely specified by the fact that it has to be bilinear in order to be consistent with probability theory. And it has to, so the product of the 2 unit effects must give the global unit effect. And this is given by this expression here. Okay. So, and we see that here when F and G are the projector onto the symmetric subspace, this is 1, all this is unit, and we just have P plus times P plus P minus times P minus, which is, sorry, is this unit effect. Okay, so it's correct. And this fully constrains this star product. Okay, so that's excellent. We have a consistent star product and it's unique. So we don't have to consider different possibilities. Once we specify this, we find this, we can also obtain the rule for calculating the reduced mixed state when Alice and Bob have a bipartite pure state. Okay, so this rule is actually just a consequence of this star product. We don't have any other options, and this gives us, yeah, how to take the reduced state, mixed state. And yeah, so, and an interesting consequence of this rule is that it violates the what in the Pavia papers called the purification principle. The purification principle tells that imagine that we consider Alice subsystem. Any convex combination of any mixture of pure states on Alice subsystem, that is any mixed state for Alice, can be written as the reduced state of a global pure state. Okay. Well, this does not happen in this theory. There are mixtures of local states for Alice that cannot be written as the kind of partial trace of a global pure state. Okay, so we have, but all these very exotic properties are actually logically consistent. This is not, in principle, you may not like it, but it's not logically inconsistent to have a theory of this sort, okay? But now we are going to find a property of this theory that makes it inconsistent. And this property is the fact that this star product is non-associative. And this doesn't make sense because the way we divide the universe into subsystems is a subjective choice, okay? It cannot make a difference on the probabilities that we predict, okay? And if this inequality happens, it means that, okay, so we have something that for some observable could be a tripartite system, but another observer could describe it as a bipartite system, where this is a single system and this is the other. And another observer could do this different bipartition, okay? And these are subjective choices in the description. It's just a change of description. It's not changing what is out there, okay? So it should not change the probabilities that the theory predicts. And hence, but in this theory, the probabilities are changed depending on how you consider the order of the star product. So, well, but that's excellent because, well, we have this theory that makes complete sense for one system, two systems, but as you go to three or more, it's inconsistent, okay? And this is, we like this a lot because it means that we don't need to regard this theory. It means that we can rule it out, okay? And then we came with the hypothesis that perhaps all alternative measurement postulates have a non-associative star product, and hence they are inconsistent. And hence the only consistent alternative measurement postulate is the standard quantum one. Okay, and this would be nice because it would mean that it is the only possibility. Good. Okay, so these are the postulates again. So now let's consider in general theories with alternative measurement postulates. So theories that satisfy this postulate, the first three, but they have another different measurement postulate. Well, the first problem is how we characterize mathematically an alternative measurement postulate. So in quantum mechanics, outcomes are characterized mathematically by POVM elements, but in general, we don't have this. So how we are going to write things in the paper? But there is one approach to this, which is the following, is that for every Hilbert space dimension, 2, 3, 4, etc., we have a set of outcomes, okay? So F is an outcome of a measurement, and big F is a set of outcomes corresponding to the Hilbert space of dimension D. Now, how can we mathematically characterize these outcomes? Well, for every outcome, the probability of getting outcome F when I prepare psi is just a function of psi. So one possibility is to characterize this outcome by this probability function, okay? So every outcome will be written by the corresponding outcome probability function. And this is a set of all outcome probability functions in this alternative theory. Okay, so we have one of these sets for each dimension. But later, for instance, if I consider, let's suppose that A and B are both 2, and then the product AB is 4, okay? Because 2 times 2 is 4. So now we have here this set tells us all outcomes of the Hilbert space of dimension 4. But here we don't have the structure of where are the local measurements. Okay, so I want to be able to locate in this big space where are the, let's say, the product effects. Okay, and this is not given by just giving the series of sets. So I need this specification additionally to have a complete theory. And this specification is given by the star product. Good. So yeah, we have now a way of specifying any alternative measurement postulate. Outcome probability functions. We call those outcome probability functions, that is OPFs. We could call them effects, but effects suggest some linear action, and some linear action in some space. But here we don't make any assumption on what is the structure of this function. Okay, this function could be non-linear, non-quadratic, anything. It can be even discontinuous. Okay, we are not making any assumption. Okay. Now we will see that just because outcome probability functions are probabilities, and hence we can do probability calculus with them, only because of this endos the spaces FD with some properties. So I repeat, outcome probability functions are just functions from the set of pure states to probabilities. And now if you take a particular Hilbert space dimension and you take some outcomes labeled by F, then you can just throw a random variable with probability PF, choose one of these outcomes, forget which measurement did you perform, and then this effectively would generate this outcome probability function. Okay, and because I effectively can make this, can simulate this, then it needs to be necessarily a valid outcome of the theory. Okay, so this implies that the sets of outcomes are convex. Another property is that in these sets of outcomes, we can define the action of the unitary group. And the way you act on an outcome F is by just composing it with F. So first we apply unitary to the state, and then we apply the outcome probability function. Okay, so this implies that every alternative measurement postulate has an associated alternative representation of the unitary group. And this is excellent because we know very well the theory of the representations of the unitary group, and we can start classifying all these alternative theories and see how they look and which properties they have. Let's just start, just to give some example of how this representation theory works. We can see that in any Hilbert space of any dimension, you can choose, for instance, this state. This is just a particular pure state. Okay. And this state, if I apply any unitary, this is a subgroup of unitaries. Okay. A subgroup, and it's a subgroup that lives invariant this state up to a phase, but phases don't matter in pure states. So this subgroup is invariant. It leaves one state invariant. Okay. So this implies that, okay, so it turns out that all representations of the unitary group can be represented by these diagrams. If you're not familiar with these diagrams, it doesn't matter. What I'm going to say, it's not, doesn't require this, okay? I'm just saying that for any representation, this is an arbitrary representation, this is another. If I restrict this action to this subgroup, it must have an invariant vector, okay, an invariant mixed state, because the space of mixed states is dual to the space of effects, okay? And it must have the invariant mixed state corresponding to this pure state in particular, okay? And these representations do not have an invariant vector, so then we rule them out automatically, okay? So, and then what are the only representations that have invariant vectors? And it's an infinite series whose weight diagrams are given by these hexagons. Okay, so this is a standard quantum mechanics. This is the one of the theory I presented before, and you have an infinite series. Okay, and if you're not familiar with this, it doesn't matter because it's very easy to understand. So all these actions, representations, are contained in this representation. This is a representation that if we take n copies of a pure state, we can act with a unitary group with n copies of the unitary group, okay? So this representation clearly preserves the invariant states when I constrain it to this subspace. And then we have that if we assume that the dimension, so if when the dimension of the Hilbert space is finite, we assume that the dimension of the corresponding mixed states is also finite, we find that with this assumption, all outcome probability functions must be of this form for some finite n. Okay, so an example was the theory that I put as an example. So yeah, this we can, so all these theories are consistent if we only deal with single systems. And we have a very pretty nice characterization of all of them, all these alternative Born rules. Good. So, but now we, of course, we're more ambitious. We want theories also to be consistent when we consider multipartite systems. This is just a reminder of the properties of the sets FD. They are, by the way, if you want to ask questions, go ahead, please. Okay, so we have, yeah, that the sets FD are convex and they have an action of the unitary group. And yeah, but now let us see the properties of the star product. Okay, these are consistency conditions. Okay, so these are not assumptions that I'm putting on top. They are included when we use the word measurement or outcome probability. Okay, so outcome probabilities are probabilities and they must satisfy the rules of probability calculus. Okay, so yeah, the star product, first of all, I can always make a measurement on this system by preparing an ancillary state on system phi and making a measurement on the ancilla and conditioning on certain outcome. Okay, so because this is something that I can always do, then this must be a possible measurement contained in the measurements of my initial system. Okay, because operationally I can implement it and I define this set as containing all measurements that I can operationally perform. This mathematical condition implies a more sensitive one. So when I prepare product states, pure states, and I make product measurements, the probabilities are product, they are not correlated. Good. Other property is that the convex structure of a system is independent of whether I consider this system on its own or as part of a larger system. Okay, so this is again the fact that how I divide reality into systems and subsystems is a subjective choice, is a description thing, is not something that is out there. Okay, so it should not change probabilities. And the same happens. The action of a unitary in a particular set of effects must be independent of whether I consider this system on its own or as part of a larger system. And the last condition, what I mentioned already, the associativity. Okay, although this is always the same philosophy that the predictions of the theory must be independent of how I consider my system as part of a larger system or a system on its own. And yeah, the partition of a system into subsystems, how I do this partition should not affect the predictions of the theory. Excellent. With all these consistency constraints, we can prove the following theorem. Okay. It states the following: the only family of finite dimensional sets of outcome probability functions, one for each Hilbert space dimension. Well, here it's only finite dimensions. Okay. The only family of finite dimensional sets of outcome probability functions equipped with a star product satisfying the previous conditions, all the ones that I wrote before, can only be the standard quantum one. Okay. So measurements are POVM elements, and yeah. So this is a proof of our claim based on the premise of this theorem are the consistency constraint. But there is an additional premise, which is that when the Hilbert space is finite, I'm assuming that the corresponding set of mixed states is also finite dimensional. Okay, and this is not a logical necessity. This is some assumption that we make because we need it to make the proof mathematically. We cannot operate without this assumption. So yeah, this assumption tells us that a finite dimensional Hilbert space has finite dimensional set of mixed states. However, this assumption is extremely reasonable, because if it's not true, you should imagine that the state of a spin 1/2 particle, in order to specify a mixed state of a spin 1/2 particle, you would need infinitely many parameters. Okay, and you could not do state estimation because you would need to estimate all these infinitely many numbers. So it would be pretty difficult to operate with theory. And it's, it's also still possible that perhaps this assumption is not necessary. It's just that we have not been able to work without it. Or perhaps that this assumption can be relaxed, and maybe we only need to assume something weaker, like the continuity of outcome probability functions. This continuity is very natural because it would tell us that if this continuity doesn't hold, it means that the topology of the Hilbert space in terms of distinguishability of states is different than the natural topology of the Hilbert space. You would have like discontinuities in terms of distinguishability. Good. This other theorem is for infinite dimensional systems, in particular countably infinite dimensional Hilbert spaces. And basically it states the same thing. Of course, here the set of mixed states is not infinite dimensional, okay? And here we use another consistency constraint that is also a logical necessity. So if to make a measurement on this system, I use an ancilla, I prepare it in system psi, and I do a joint measurement, this is clearly one possible way to do a measurement on our original system, okay? So it must be then, it must belong to the set of all possible measurements. Okay, and this must happen when the two systems, A and B, have any possible pair of dimensions, including countably infinity. Okay, so yeah, so we conclude that the quantum measurement postulates are the only consistent ones. Until now, I haven't talked about the state update rule, but actually, even before our work, this was already known, that the only consistent state update rule compatible with the Born rule is the quantum one. Okay, so it's not even our work that that's the only possibility. Okay, so I'm not going to spend time on this. Okay, so I'm finishing now. These are the conclusions. The standard measurement postulates are the only possibility compatible with unitary quantum mechanics. Our work can also be seen as a derivation of the Born rule. There are many of those, Gleason's theorem, etc. But our work has certain advantages. One is that we don't assume any structure of measurements. Okay, for instance, Gleason's theorem assumes a structure of measurements, namely orthonormal bases or POVMs, depending on which version you take. But it's not that we don't need this assumption, is that we also derive this. In addition to the Born rule, we derive the structure of measurements. Also, some other deviations, like in many worlds and Zurek's invariance approach, they make unconventional uses of probability in the sense that they apply probabilities to branches in a deterministic universe. I mean, I like these derivations a lot, but they make an unconventional use of probability. And yeah, we don't make any other assumptions. For instance, in Gleason's theorem, you assume some sort of non-contextuality in the sense that it is that the outcome, the probability of an outcome, it's independent on which measurement this outcome belongs to. Okay, sorry, if you're familiar with Gleason's theorem, you will understand what I'm talking about. It's just an assumption. And I just want to finish this presentation with the following sentence. The specification of the mathematical structure of measurements, outcome probabilities, and post-measurement states should not be understood as postulates, but rather as theorems. Thank you very much.
That's great. Thank you so much. Sorry, my camera's not turning on. Okay, great. Thanks very much. That was a really interesting talk. So once again, open the floor to questions. So I've been asking quite a lot of questions, and I would just encourage younger people in particular, so masters and PhD students, anyone early career, if you've got a question, please raise your hand. Well, you can take another moment and think on it. I do have a question. This is a very fascinating way of reducing the number of assumptions that we need to put into quantum mechanics. And my question is basically, does the same logic work if we do it the other way around? So if rather than taking, that we want probabilities to be bounded in this way, we want our products to be associative, this kind of stuff. If we say we start with the Born rule and the measurement postulates, can we derive instead those aspects of quantum theory?
Can we derive, you mean the other postulates or these consistency constraints? What do you mean?
So you take a number of a number of consistency constraints and use them to derive the Born rule and measurement postulates. Can we instead say, if we take as given the measurement postulates, can we derive that these consistencies have to hold?
Well, the quantum measurement postulates, they automatically satisfy all of them, so you can derive them for the particular case of quantum measurements.
Okay,
they satisfy straight away all this.
We also have a question in the chat from Ajit Singh. Would you consider projective Weil-Heisenberg representations like Schwinger operator base?
Like which operator base?
In the Schwinger operator base.
Ajit,
if you'd like to unmute yourself, you can ask the question more thoroughly yourself.
See, what I mean is, you take G1 and G2 elements of group and UG1, UG2 corresponding unitaries. Then U of G1, G2 is a scalar multiple of UG1, UG2, and scalar is of modulus 1. And this is what happens in Weil-Heisenberg representations coming from Schwinger bases.
So is what you are saying that we only need to take into account projective representations?
Yes. That is what I mean by saying projective representation. That it is a sort of, you can multiply it by a scalar of modulus 1.
Yeah. So projective representations are, I don't know how this goes. In a sense, we should be considering projective representations only.
And another thing is anti-unitaries also. Rather than unitary operators, you can take anti-unitary operators. Anti-unitary means UF, UG is inner product GF rather than FG.
Sorry.
They are called anti-unitary.
Yeah.
What will happen in those situations? That is what I wondered, and I asked.
Okay. So we are not considering to expand the action with anti-unitaries. I suppose this will give us more constraints, so I think it doesn't change the conclusion in this case. Now I don't know how to argue this, but I understood that our consideration included all possible. Yeah, because the unitary action on the Hilbert space is projective. Okay, so in a way we are only considering projective representations. But these can be found in the standard representation family as well, in the linear representation family.
We've got, thanks very much. We've got time.
And another thing that I asked was, there is product system, lot of theory developed on product systems. And that was done by Arveson in 1980s. And Rajaram Bhatt has done further work on product systems and many other people also. So because you are taking FAs, A's varying, and then FA tensor FB, and they are all concerning those product systems. Arveson, William B. Arveson, who developed a lot of theory of completely positive maps.
What is a product system?
Product system, you take P projection PA in space CA, projection PB in space CB. Then you take CA tensor CB.
Sorry, I'm just gonna interrupt for a moment. We've got I think that if there's a more involved conversation, we can continue that in the break after.
I'm very happy to discuss. Yeah.
Excellent. And thank you for the question. And thanks for the response. I think we've got just about time. Lucas, if you want to jump in with another question.
Yeah, thanks a lot. First of all, thanks a lot for a very interesting talk. I have a very short question regarding your assumption on finite dimensional OPF sets, just so that I get it right. So you basically assume that the set of states is finite. So even the set of pure states is not a continuous set in that sense, but is somehow discretized?
No. The set of pure states is a standard projective Hilbert space. I'm not changing that. Now, associated to the set, for every Hilbert space dimension, you have the corresponding set of mixed states. Okay, and how many parameters in quantum mechanics? The number of parameters to describe a mixed state is, instead of for pure states, is 2 times d. Okay, well, minus normalization and phase, and for mixed states is order d square. Okay, but this can change. Okay, if you change the Born rule, then you also change the structure of mixed states, the set of mixed states, and in particular, its dimensionality. Okay. For instance, in the example theory that I put, the set of mixed states has a dimension higher than d square. Is much bigger, but still it's finite. Okay, so this assumption tells that for every Hilbert space dimension, if for any finite dimensional Hilbert space, the corresponding set of mixed states can have any finite dimension, but it has to be finite. Okay.
Oh, I see. So this is absolutely fulfilled in quantum mechanics.
Yeah, of course.
Oh, I see. Okay. And if you have time, maybe for another short question, I had the impression that your consistency conditions are basically conditions for an agent how to reason about the
exactly
world.
Yeah.
So how does this fit into this cubism approach? Have you thought about this?
I think that precisely. I mean, our these consistency constraints take some perspective, like an operational perspective, and I think that this is a very wide perspective, and cubism fits perfectly inside. I mean, cubism also, as you say, takes this agent point of view, and yeah, I suppose that they are going to assume that the way you partition a system into a subsystems, which is a subjective choice, is at least it's not given by the theory. Okay, so if it's not given by the theory, it means that you can do it in any way you like. So this should not change probabilities. So I'm not an expert on cubism, but I think that they are going to be very happy with these conditions.
Okay. Yeah, exactly. I also see an overlap. That's okay. Thanks a lot.
Thank you.
Okay, great. Thanks so much, Lluis. Really interesting
Thank you.
talk.